In this sixth module, we've been discussing weak interactions, and we now turn to the Higgs mechanism. In this 11th video, we will introduce the dynamic generation of particle masses by this mechanism. After following this video, you will know how to argue that mass cannot be an intrinsic property of particles, how what is called mass can be dynamically generated, and how the Higgs mechanism implements this through the interaction of particles with the omnipresent Higgs field. And finally, you will know qualitatively how particles evolve in a vacuum filled with a Higgs field. What is the mass of an object? There are two phenomena connected to mass. First, mass is the property of an object which opposes itself to acceleration according to Newton's law. This is called the inertial mass. At the same time, it is the property of an object which allows it to attract other bodies via gravity. This is called the gravitational mass. It is the equality of these two properties which led Einstein to formulate general relativity, the only theory of gravitation known to date. But it is only the inertial mass which is of interest here. The gravitational interaction is too weak to matter at the subatomic level. One measures the mass of a particle by observing the energy that it takes to create it at rest, or by observing the invariant mass of its decay products, or by observing its velocity at a given energy. It is in fact this last property of the mass that we must retain. Mass is the property that keeps particles from moving at the speed of light, no matter how energetic they are. The particle spectrum that you see in this graph is extremely large, both as far as matter is concerned, with a neutrino weighing of the order of a milli-electron volt, and up to the top mass, which is about 107 giga-electron volts. It's also true for forces, where the mass of the photon and of the gluon is 0, and the spectrum goes up to the Z and the W mass of 90 and 80 GeV, respectively. We believed, me and probably also you, that the mass of elementary particles, quarks and leptons and gauge bosons, was one of their intrinsic properties, like the electric charge, the color, the flavor, the baryon and the lepton number. But this is not true. Mass is the product of a dynamic process, without which the mass of all the ingredients of the universe would be 0. Let us trace back the origin of mass across different scales. For ordinary matter, solids, liquids and gases, the mass is to a good approximation equal to the sum of the masses of their atoms. The cohesive energy, for example, in a crystal is between 1 and 10 electron volts per atom, which is small compared to the mass of the atoms. The mass of an atom is also pretty much equal to the sum of the masses of its electrons and its nucleus. The atomic binding energy is of the order of 5 to 25 electron volts per electron, small compared to the mass of the nucleus. This reasoning continues to be true at the nuclear level. The nuclear mass is not far below the sum of the masses of its nucleons, but with the more important binding energy, obviously, as we have seen in module 2, the binding energy is of the order of 8 mega-electron volts per nucleon, but it is still small compared to the mass of the nucleon itself, which is of the order of giga-electron volts. In summary, the mass of the matter in the universe is dominated by the mass of the protons, the neutrons and the electrons which populate it. But at the scale of the nucleon itself, this reasoning does not work anymore. Proton and neutron contain low-mass quarks and massless gluons. The nuclear mass is dominated by their binding energy. It already has a dynamic origin. But quarks and electrons do not have binding energy because they are, as far as we know, point-like particles. They have no substructure, so there is no binding energy involved. So, at least for them, could mass not be an intrinsic property? The answer is no. And the reason for this is quite subtle and fundamental at the same time. Continuous symmetries are closely linked to the conservation of a physical quantity by Noether's theorem. You see Amélie Emmy Noether as on this photograph. In particular, gauge symmetry, the invariance of observables relative to a local phase change of the field, is the basis of the standard model of electroweak and strong interactions. Gauge symmetry is in fact necessary to ensure the regularization of infinities in a field theory, allowing to absorb them into measured quantities. Without this possibility, the standard model would not make any predictions, yet it agrees with experiment everywhere. On the other hand, an intrinsic particle mass, for matter as well as for forces, violates gauge symmetry. For a massive field, we do not have the freedom to change its gauge. In other words, the fact that all generations of matter in all families have a different and non-zero mass, and the fact that mz and mw are not equal to the photon mass, namely not equal to 0, violate gauge symmetry. Consequently, mass must come from a dynamic process instead of being an intrinsic property that particles are born with. Why can we not simply treat the T quark as a heavy U quark and the Z boson as a heavy photon? The problem comes from the propagation probability of heavy bosons. The probability amplitude for the exchange of a zero-mass photon between two vertices is proportional to 1 over q squared, with q the form momentum of the photon. This amplitude is thus inversely proportional to the invariant mass squared of the virtual photon. It has a pole at q squared equal to 0, the mass of the real photon. The amplitude gently tends to 0 for q squared going to infinity. For massive bosons, on the contrary, the propagator amplitude is proportional to 1 over q squared minus m squared. It has a pole at q squared equal to m squared. For ordinary reactions, this does not cause problems to first order because they occur at a fixed q squared. However, this propagator causes serious problems for higher order processes, as in the case of two boson exchange shown in this Feynman graph. Inside the square loop, conservation of energy momentum does not limit the circulating form momentum. Any q of one boson is compensated by minus q of the other. To obtain the full amplitude of this process, one must integrate over this internal momentum to infinity, and this integral diverges. The same is true for the propagator of the virtual fermion in the loop. A finite mass will make the amplitude diverge. The intrinsic mass of bosons and fermions, which destroyed the gauge symmetry of the theory, thus also makes it unusable. Both facts are indeed intimately linked, as was shown by 't Hooft and Veltman, which were decorated by the Nobel Prize for this discovery in 1999. This is not the case, however, if mass is a dynamical phenomenon. The Higgs mechanism invokes a scalar field to keep particles from moving at the speed of light. This way they appear massive to us, even though they aren't. If massive fields are incompatible with gauge symmetry, then the opposite should also be true. Symmetry breaking should make an originally massless field massive. To understand this intuitively, we again use a mechanical analogy. Imagine an infinitely fine needle as shown in this picture. It has no momentum of inertia about its axis. Now we apply a coaxial force beyond the elastic limit of the needle. At first, nothing will happen. The system remains in unstable equilibrium. Through a small quantum fluctuation in the crystal lattice of the needle, it weakens in a random place, and the needle folds in a random direction. The cylindrical symmetry of the system has spontaneously disappeared. At the same time, a moment of inertia about the original axis has appeared. The system has acquired a kind of mass it did not have before. In a quantum field theory, a similar effect occurs if the ground state of a system does not possess a symmetry that is present for the system in general. Let us consider a system with a single complex field phi, where the minimum of the energy is plotted here as a function of the real part of phi and the imaginary part of phi, where this minimum of energy does not match phi equal to 0, but occurs at all states with phi squared equal to v not equal to 0. The ground state of such a system is not the vacuum, with all fields equal to 0, but a space-time filled with phi everywhere. If we want to do a perturbative calculation in such a vacuum, we need to choose a minimum of the energy around which we will develop the states. By choosing a specific value of phi as the ground state, with phi squared equal to v, because that is the minimum of the energy, one breaks the symmetry with respect to the phase of phi. This is called a spontaneous symmetry breaking. At the same time, the field phi itself and any other field interacting with it acquires mass. We call such a field phi a Higgs field. How does a particle move in a vacuum filled with a Higgs field? All fields which interact with their field phi with a given coupling constant are constantly kept from moving freely. They propagate like in a viscous liquid. Their speed is lower than c. They have a mass they would not have in a real vacuum with a Higgs field absent. Let me demonstrate this effect by, again, a mechanical analogy. I have here two test tubes, one filled with water, one filled with olive oil. If we look at balls falling through the liquid, here there are two balls in the liquid. One is a clay ball, the other one is a steel ball. We of course see that they fall with a different speed because they have a different interaction with the liquid. The porous surface of the clay ball makes it fall much slower than the smooth steel ball. So this would correspond to different particles moving in a viscous liquid so that they do not fall at the speed of free fall. If we change the liquid, in other words, if we make a stronger Higgs field, both balls will fall more slowly, but it is still true that their individual speed, their individual apparent mass, is given by their coupling to the field, by their coupling to the liquid. So this is analogous to the Higgs mechanism. The strength of interaction, the strength of presence of the Higgs field is proportional to, is analogous to the properties of the liquid, and the coupling of the different particles to the Higgs field determine with what speed they move, even though their mass is zero. So the mass of particles is given by their coupling constant with the Higgs field. It is dynamically generated through interactions with this ubiquitous field. In the next video, we will discuss the quanta of the Higgs field, the Higgs bosons.